All right, Chem 1110 students, we're about to finish Chapter 6. We're going to look at three remaining topics: formal charge, resonance, and octet rule exceptions. So with Lewis structures, we can calculate formal charges. Formal charges are not real charges. They are a bookkeeping method to help us figure out which of some possible structures is the most plausible structure. Formal charges are calculated by taking the valence electrons and subtracting the associated electrons for the element in any given structure. So those include the non-bonding electrons and half of the atom's bonding electrons. So they're the ones associated with the other atom. So if we look at ozone, I'm going to look at determining the formal charges. And in this case, we have one structure, but if we had more, we could use formal charges to pick the better structure. So we have three oxygens. The one on the left and the middle one are double bonded. The middle one is single bonded to the one on the right. And you can see how I calculated the associated electrons, and I've tabulated them below with the valence electrons, and I take that difference, and that's my formal charge. So the oxygen on the left has a formal charge of 0, the one in the middle is +1, the one on the right is -1. So the overall charge is 0, and it's very important that that overall charge matches the actual charge on the molecule, which in this case is neutral. Here's an example of looking at the nitride ion. This little discussion is talking about how the body can take nitrate and convert it to nitrite, and this interferes with the ability of hemoglobin to transport oxygen, which is extremely important, for continuation of life. So we follow the 6 steps to draw the Lewis structures of the nitrate ion, and that is shown here in the middle of the slide. And I talk about how you actually find those associated electrons in that text below. So what we see is that the nitrogen has a +1 charge, the singly bonded oxygens are each a -1, and the doubly bonded oxygen is 0. So when you add those up, you get a charge of -1, which is what nitrate has on it. So formal charges may not be true charges, but they are very useful to us. All right, so if there is more than one possible structure, we can determine the best arrangements by a Lewis structure where all the formal charges is 0 would be the best. We'd prefer to have small formal charges than large ones. And the formal charges that we find need to be consistent with the electronegativities of the element that we're talking about, whether it's fluorine or boron. So I have an example here at the bottom of the slide of CO2, 2 potential structures where the octet rule is met in all cases. And so we're going to compare the formal charges for the one on the left, which has 2 double bonds, to the one on the right, which has a triple and a single bond. And you can see that for the 2 double bond structure, the formal charge is 0. The formal charges are all 0, whereas the triple bonded structure has a +1 and a -1. So the structure with all 0s for formal charges is definitely the preferred. Okay, so here's an example where we're going to look at formaldehyde. There are 2 potential structures shown, and we want to determine which is the best structure. So in order to do that, we complete the Lewis structures from those skeletons, putting in the double bonds and the non-bonding pairs of electrons. And then we look at the formal charges. So in the structure on the left, the hydrogens have a formal charge of 0. The carbon atoms are -1, and the oxygen is a +1. So we see formal charges there at the bottom of 0, -1, +1. Excuse me. If we look at the structure on the right, the hydrogen has a formal charge of 0, the carbon has a formal charge of 0, and the oxygen has a formal charge of 0. And so therefore that is the preferred structure for formaldehyde. All right, and so there's just a little discussion here, you know, and there's something to think about, and that is that in the one structure we had a positive formal charge on the oxygen, which is inconsistent with its high electronegativity. All right, so now we're going to talk about resonance. And a resonance structure is one where one or more Lewis structures, 2 or more Lewis structures, don't represent it very accurately. And I've got some examples here. One is ozone, and so the double charge can be on the left, or the double bond can be on the left, the double bond can be on the right. And we use a double-headed arrow to indicate that the molecule is actually going back and forth, or there is an average structure, which is not something we can readily draw. Another thing to realize then is that resonance structures are just a human invention. The molecule actually knows where it exists. And so resonance structures only differ in the positions of the electrons, not the position of the atoms. So we have carbonate, which is another example. We have that double bond moving around between the different carbon-oxygen pairs. And benzene is another big one for showing resonance, where these double bonds just shift a spot. And of course, those electrons aren't truly moving back and forth, but you have, between 2 of these positions, sort of instead of a double bond, it's a 1.5 bond. All right, so in this example, we're talking about the problems with burning coal, and that has to do with the production of sulfur dioxide, which in the atmosphere can become sulfur trioxide, and with combination with water in the form of rain, it produces acid rain. So what we're going to do is we're going to draw the Lewis structures and try and determine the correct one for SO3, and we get 2 sulfur oxygen single bonds and 1 double bond, as shown here at the bottom of the slide. But that double bond, just like the carbonate, can actually move around, and so we put double-headed arrows between those, showing that this is a resonance structure, and we recognize that the true structure for SO3 is some average between those 3. So once again, we're just talking about a difference in the position of the electrons, not the atoms. All right, and our final topic is exceptions to the octet rule. We start out by learning the octet rule, but there are many situations in which elements like an incomplete octet. And there are 3 different categories. The first one is where that central atom has fewer than 8 electrons due to a shortage of electrons. So beryllium hydride only has 4 total electrons in the system. Beryllium has 2, each hydrogen has 1. And so this is, a group 3A element. And so they are pretty content with that. The hydrogen has an isoelectronic structure with helium. Beryllium is pretty content to just have those two bonds. And so another example is boron, which is over 1 in the periodic table. And in this case, boron is pretty happy just to have 6 electrons. It has 3 valence electrons, so it forms 3 bonds and has 6 electrons around it. The second case where we may have exceptions to the octet rule is where the central atom has fewer than 8 electrons because it's got an odd number of electrons. And an example that I have here is nitrogen dioxide. There's 17 valence electrons in this system, so there's no way to pair them all up. Molecules with an odd number of electrons, that odd electron is often called a free radical, and they are extremely reactive because they're looking for another electron. Okay, and then the last one is when the central atom can have more than 8 electrons, and we call this an expanded octet. So we have several cases. This one is a sulfur hexafluoride. Sulfur actually has 6 bonds, which means there's 12 electrons around it. So this is only going to refer to or apply to atoms that are in the 3rd period or beyond. And that is because they have not only 3s and 3p orbitals, which would hold 8 electrons, but they also have 3ds that can be used in bonding, even if they're not used just to build the atom. All right, so here's an example. We've got several here. We're going to draw the Lewis structure for boron triiodide. It's a very simple structure. There's only a total of 24 electrons, 3 from the boron and 7 from each of the iodines. We subtract 6 electrons for the 3 bonds. It leaves us 18 to distribute as lone pairs, and they go around iodine, and the boron is very happy with just 3 bonds. Now, it's interesting that we could actually make some additional resonance structures by moving a pair of electrons off an iodine and forming a octet around boron. Those are possible resonance structures, and so in this case there's 4. Another example is arsenic pentafluoride. So this is an expanded octet. This is how you would have to draw arsenic pentafluoride, putting 5 fluorines around the arsenic. And what you actually have are the 2 fluorines on the left are in the same plane with the fluorine on the right, and then the other 2 fluorines are above and below that plane. I've told you how many valence electrons you have here because arsenic is in row 4, so it has D and F orbitals that can be used to do this expanded octet. And everything except for arsenic ends up with an octet and is pretty comfortable with that. All right, then we have xenon tetrafluoride. This is an interesting one because there are 36 total valence electrons, 8 from the xenon. It's a noble gas. We don't normally think of those reacting, but it will in this case. And so we end up with 4 electrons left over after everything has an octet. So we put the extra 4 electrons as lone pairs on the xenon. All right, and the final one is the structure of sulfurous acid. And I'm going to let you all just take a look at that so that we don't run over on this video. And there's some interesting points here You don't want too many double bonds because atoms are not comfortable with it. And we have completed Chapter 6.